Welcome to Training Module 2 for the ODOT Active Transportation Benefit Cost Analysis tool. In the previous module, we discussed what benefit cost analysis is and when to use it. We also provided an overview of the BCA tool, including its setup, the benefits and costs it measures, and a summary of the needed inputs and where and how to enter them in the tool. In this module, we will walk through the BCA tool with an example active transportation project. We will go through each of the inputs and take a look at the results. We invite you to follow along and fill out the spreadsheet for practice. So let's jump into our case example. Let's say there's an intersection with a history of crashes. To address this, state and municipal planning partners would like to install a rectangular rapid flashing beacon, or RRFB, and want to know whether the project would be of net benefit. Additionally, the community is considering building a new shared use path for people walking and biking along the same arterial corridor. Because the tool is designed for one project at a time, this example will involve two versions of our spreadsheet and then adding results up at the end. At first glance, these active transportation projects look like a great fit for our BCA tool. Let's first think through a few things. What are the anticipated benefits? Do they align with the BCA tool's benefit categories seen on the left? Safety? Yes, we have a demonstrated history of crashes, and the RRFB should reduce these. We also expect safety benefits from the path, but we don't really have recent crash data available, so we'll address this using the amenity benefits calculations. Travel time savings? In this case, we expect the new path will make people feel more comfortable walking and biking, and so they will choose to use it to reach nearby destinations rather than driving. They will be willing to accept slightly longer travel times because they value the opportunity to use a comfortable, safe facility that will provide easy access to neighborhood businesses without the hassle of parking. Vehicle operating cost savings and emission reduction? Yes, when people can walk and bike instead of driving, they will spend less on maintenance and fuel, and there will be fewer harmful emissions. Avoided highway externality? Yes, less traffic means less noise, more safety, and less congestion for the community. Amenity benefits? Yes, these are key here. The path's users will benefit from improved quality and comfort of their journey along the new dedicated facility. Evaluation of this will be based on the type and dimensions of the improvement. Finally, health benefits? Yep, some of the people who walk and bike because of the project would be engaging in new cardiovascular exercise, leading to associated improvements in health. Great, so this example aligns well with the BCA tool's offerings. And now we also have a mental map of what outcomes to expect from our analysis. So, what data do we need? What data do we have? Let's revisit the tool setup, which we examined in the last module. Here's a diagram of the tabs in the BCA tool. Recall that we should only need to interact with a handful of these. We have our Project Info tab, which has just a few items to enter. We have our Inputs tab, which will be our main interface for entering project data for the no-build and build conditions. And then we have our Safety Amenity toggle, which we'll talk about more in a little bit. We'd also like to use our red optional data tab, Safety Inputs, to analyze reductions in crashes from the rectangular rapid flashing beacon, using the data we have from recent years on crashes at that intersection. We'll analyze the rectangular rapid flashing beacon first. Let's start in our Project Information tab. We need to add data in these green cells. This information will apply to both components since we're assuming the same timing within an overall project. First, we have the first year of project development or construction. Our project construction should begin in 2026, and it'll take 5 years to build. The last input here is for the operational period. How far into the future do we want to project for the purposes of this BCA? How long will this improvement continue to generate benefits? Let's say 25 years, and we can always return to this to see if BCA calculations change depending on our window of analysis. All of the gray cells populate based on what was entered. Great, so let's move on to the main Inputs tab. We again see all these green input cells. We enter our project name, RRFB. We see our construction and operation years based on the last tab we completed. Great, nothing to change here. And now we have some cost info we need to enter in boxes 1.06 and 1.07. We have estimated that construction will cost $38,000, and we do not expect any meaningful increase in operations and maintenance costs, so we leave that zero. For more information about how to estimate project costs, please see the third video in this training series, which covers the cost opinion tool. Then, we have compound average annual growth rate of trips. What's this about? As you see in the notes column, this variable represents the overall growth rate in trips across all modes, assumed to be the same with or without the project. In our region, background population growth is about 1% each year, so we enter a modest 1%. Now we can move on to box 2, roadway characteristics. For each of these green input cells, we see a no build and build input. What happens if we don't build our project? What happens if we do build it? We must have both these scenarios data to properly measure the net benefit. For traffic speed on the roadway, we know that the speed on the arterial is 35 miles per hour. This project is not implementing any traffic calming to reduce speeds, so we expect the same speed both with and without the RRFB. We also need to enter AADT, average annual daily traffic. It looks like it would be unchanged, no volume reduction benefits here. It'd be 20,000 trips in both scenarios. Great, let's move on to box 3, sidewalk and pedestrian improvements. Not all active transportation projects will need to have data for this box. First, we need the average number of daily walking trips with and without the new flashing beacon. We've entered that there are 50 trips per day with or without this improvement. We're not modeling the path right now, so we leave the sidewalk inputs at 0. This is a good time to note that some variables may be irrelevant and be zeros. We are not analyzing any cycling infrastructure, so we leave everything blank on box 4. Now we move to our Safety Inputs tab. This is critical for this project component. We are proposing a new rectangular rapid flashing beacon. With this improvement, we anticipate a reduction in the crashes we've seen at this intersection in the past. There are 2 data points we need to enter, a countermeasure and then historical crash data. First, the countermeasure. You'll see at the top instructions to select a countermeasure. In this cell, you'll find a drop-down list of different countermeasures that have an already calculated impact on crash rates. Most common active transportation countermeasures will be in this list. In our case, we have Install RRFB, so we select that. If you can't find one that specifically captures your project from the drop-down, then you do have the option to override the applicable crash modification factor, using something you found in the FHWA CMF clearinghouse, for example. Please make sure you have a separate version of the spreadsheet saved before you override the fields, because this will make the drop-down selection option no longer work. The countermeasure we select will determine what % reduction we'll see in the crashes, which is why we need historical crash data as a baseline. So, in these green cells, we have traditional CABCO categories for 2 types of crashes, pedestrian and cycling. CABCO is a scale used by law enforcement to report the observed severity of the victim's functional injury at the crash scene. K means killed, A is incapacitating, B is non-incapacitating, C is possible injury, and finally O, no injury. So, let's enter historical crash data. If you need crash data for your project area, you can use the AASHTO Safety tool through ODOT, available at the link shown at the bottom of this slide. We enter 5 years of data, and then the tool calculates an average annual rate of injury by category. In this case, the CMF for RRFBs only applies to pedestrian crashes, so we can leave the biking section blank. Note that the CMF shown is 0.53. This means that with the RRFB, we expect 53% of crashes to remain, or a 47% reduction in crashes and injuries in the build case. Now, because we have safety inputs, we could encounter a challenge if we were also calculating amenity benefits for the same feature. Amenity benefits are related to safety, as perceived safety provides an amenity to end users as they enjoy the improvement. This BCA takes into account this double counting issue by prompting us to select one or the other. This tab compares the benefits for the amenity benefit versus the safety benefit for pedestrians and cyclists separately so that we can choose the highest value. The spreadsheet recommendation will show the category, safety or amenity, with the highest value, and then we can follow that recommendation by selecting one or the other in the green cell. In short, it's best to ensure that the green cell has the same benefit type selected as in the cell above. Here, there are only safety benefits, so that's what we select. Now that we've made our selection, our final calculations will show the best case numbers for calculating the total benefits, but without double counting anything. From here, we can go to the Summary and Results tabs. We've completed our inputs for the first component, so now it's time to see interim results. In our Summary by Benefit, you'll see the summary total of costs and benefits by categories. These are pulled from calculation tabs that used our raw inputs to calculate. You can consult these tabs as needed if you want to see calculation formulas, but right now we're interested in the high-level numbers we see here in the summary table. The results in this case are very simple. We only see safety benefits. Now we move to the Final Results tab with the summary for this first component. We find those same total discounted benefit and cost calculations, and derived from these we have our net present value NPV and benefit cost ratio BCR. The NPV is simply the total discounted benefits minus costs. And for BCRs, a value greater than 1 means that benefits are greater than costs. In other words, the project seems like a worthwhile cause. If the BCR is less than 1, then the costs outweigh the benefits. For component 1, the rectangular rapid flashing beacon is quite inexpensive, given its effectiveness at reducing crashes, so we've got quite a high BCR ratio, making the investment more than worth it. Now we're going to walk through the same process but for our second component, the shared use path. We set up the Project Information tab in the same way. We need the same analysis period so that results can be added up at the end. We're assuming these two components will be built together as part of one construction project. These Box 1 inputs look similar, except that now we have a different capital cost for the trail of about $4.2 million, as well as an increase in operations and maintenance costs annually of $12,000. We have inputs in Box 2 that are identical to before since they're relating to the same arterial corridor. Now, Box 3 is where we start entering data related to the path itself. Since our path is shared use, we anticipate people walking and biking. That means we'll need this box and Box 4 for cycling improvements. So, Box 3 first, we need average number of daily walking trips with and without the path. We've entered here that there are 200 trips per day without the project, and we estimate an increase to 400 with the improvement. For more information about how to estimate the number of trips with a project, please see the 4th video in this training series, which covers trip estimation. Now we need the length of the sidewalk, in this case 4 miles. Note that we are calling it a sidewalk to make sure the tool calculates amenity benefits for people walking, even though we know it's actually a shared use path. We also need to know the width and average slope. These will impact the amenity calculation since walking on a narrow, hilly path is less pleasant or valued than a wide, flat path. Our no build is no existing path at all, so we put 0 for no build width, and then the path will be 10 feet wide. And for slope, let's say our improvement is flat, so 0% incline for no build since there's no path to begin with, and we'll keep it 0% since our improvement is flat anyway. There are 2 more inputs here related to marked or signalized crosswalks on roadways with a certain daily volume threshold. While we are going to install the RRFB, we already analyzed that separately, so we will just keep these at 0. Now we can move on to Box 4, cycling. Since our project is a shared use path, as we mentioned, there is a distinct cycling benefit in addition to the pedestrian walking benefit. First, we have the average number of cycling trips per day, just as we had with the walking component. Our data says there are 20 cycling trips per day without the new shared use path, but with the shared use path, we expect 30 trips. The other variables here relate to the improvement's characteristics, but not all of them apply. Does our project have sharrows? No, so let's enter zeros. Dedicated bike lanes? Nope, this is a shared use path, not a bike lane. Cycle track? No, this is a path. Paths with or without at-grade crossings? Yes, our 4-mile path does have at-grade crossings, so we input 4 for the build scenario. And the no-build scenario where there's no path, we have no miles, so we enter 0. That's it for the Inputs tab. We will leave everything blank on the Safety Inputs tab for the Path component analysis. We will make sure that we are selecting amenity benefits on the toggle. Now we will look at our second set of results. We see that for the entire operation period through 2055, we have some negative values, our disbenefits. We have additional O&M cost, as well as travel time costs for people who switch from driving to walking and biking. On the positive side, we have benefits for vehicle operating costs, emissions, avoided externalities, amenity benefits, and health benefits. The spreadsheet sums results across the years for both undiscounted and discounted values. Undiscounted means treating each year equally. We value the benefits in 2055 as much as we do the benefits in 2031. But in economics, we often apply a discount rate to give more weight to the near term. So here you see smaller discounted values each year into the future. On the far right of the table, we find the total benefits, discounted and undiscounted, across all benefit categories. Not shown here, but also in the Excel file, is a table summarizing capital costs by year. The Results tab shows that for the path alone, we actually do not have benefits exceeding costs. We are only seeing a 0.5 benefit cost ratio. Our final step is to add the results from our 2 project components. Here, we are adding up the discounted sums across all years for each benefit and cost category and each component. We do this by copying over values into a new Excel tab. As you can see, once our components are combined, we now have benefits exceeding costs for an overall ratio of 1.18. So that's the BCA tool in action. If you have more detailed questions about the input variables, or you need to alter any assumptions in the calculations, you can consult the manual and calculation tabs. Up next in our training module is a walkthrough of the cost opinion tool. This can be used to estimate project costs. Thanks for joining. For more information and resources, please visit the ODOT Active Transportation page at the link shown here.